So we move to the next speaker, and I hope he's going to be live because he's live from Australia, so it's far away. Are we ready or not?
So that's yes, I'm ready.
Oh, John is live. Excellent.
Yeah,
Hi, John. How are you?
I'm ready.
Fantastic.
Excellent.
I'm doing fine.
We don't see you yet, so maybe it's the picture is going to show up sooner or later. So John Martinez, yes. Probably everybody knows John Martinez in the quantum world, maybe beyond the quantum world, not. But so John, I will introduce you, and then we will do your presentation, and then we'll have a couple exchanges with you. We know two main things about you. Recently, you joined SQC as a researcher based in Australia, so it's a spin-off from UNSW, working on silicon qubit. I hope we're going to hear a little bit about this move from you, because researchers in that space, both in the superconducting and the silicon qubit space, are very anxious to know why this move and what's behind that. But you're famous for all the work you've done in the superconducting qubit world, I mean, for at least 2 decades, if not more. And you worked at UCSB, then you moved in Google between 2014 until last April, if I'm not wrong. And you're part of the famous team who built the so-called quantum supremacy with the Sycamore architecture. So that's where we are. And there's a small precision we should add to your bio, which is you spent a couple years here in France at Saclay, working with Daniel Estève, probably I think it was more than 20 years ago, as a postdoc, working on superconducting qubits. So that's your link with France, and we are lucky to have you here. So I hope you're ready, and you can start your presentation, and then we'll come back to you later with many questions.
Great, yes, and I can answer questions about the move and what's going on maybe in the Q&A session. Okay. And indeed, I'm very pleased to give this talk to France because I did do a postdoc in the Quantronics group in the Saclay, as you mentioned, where we did some of the foundational experiments, physics, on figuring out the superconducting qubits. And it's just been an amazing kind of professional career where I and many other people have taken it from basic science to actually building a powerful computing machine. And that's been a real pleasure for me to do that. We did this experiment in part because people have been talking about the powerful quantum computing for more than 3 decades right now. And although I think physicists believe that this eventually could be done, I think there are a lot of computer scientists and electrical engineers, and more importantly, Silicon Valley executives and government funding people who, don't understand quantum mechanics as well as we do and wonder whether this is ever going to come to a powerful state. And that was the point of this experiment, is to just show that you can build a powerful quantum computer. It makes sense, and you can do that. And thus, help the field, help everyone in the field do this with hopefully more funding and more effort and more people coming into it. And the quantum supremacy experiment is really quite simple. Basically, we run an algorithm for about 200 seconds. And then to check if the algorithm's running properly, we have to run it against a classical computer. And that would take, thousands of years to check it. If you could do that. So showing that there's this big gap between what you can do with quantum and what you can do with classical. And of course, the big reason this is working is we're computing on a very big computational space, parallel space, to the 53 or 10 to the 16 states. To get this to work, we had to do some new design. We had to get low errors, and I'll talk about that. And a little bit at the end where, this is really exciting because we should be able to do powerful, more powerful quantum computing than what we've done in the past. We still have to do something useful in the end, but we're making progress towards that. Just very briefly talk about this parallel processing of a quantum bits and quantum computer. And the basic idea is using quantum mechanics, you can encode information not just as bits, which are a 0 or a 1, but it can be a quantum state where it's 0 and 1 at the same time, where you can take that state and run it through your quantum computer and you're going to kind of compute what happens with 0 and what happens at 1 at the same time. Now, for a qubit, that's a factor of 2, maybe not such a big deal. If you have 2 qubits, then there are 4 possible states you can be put into a superposition. Now you've doubled the amount of parallel processing, 3 qubits 8, 4 qubits 16. So you see the amount of processing power, if you like, parallel processing power is growing exponentially with n. So by the time you get the 50 qubits to the 50 is big enough processor to start competing with the supercomputer. And then by the time you get to 300, that's more than states and atoms in the universe. Of course, you only get n bits, 300 bits output out of this. So you have to choose and develop very sophisticated quantum algorithms to take advantage of this. So it's not for every classical algorithm. So we're building superconducting qubits, and we think there's a fundamental advantage to them. That's very nice, is that they're macroscopic devices and relatively, let's say, easy to build and control. And you can see in this picture here that we have little wires coming in here that can control the device. And the wires are much smaller than our qubits, and thus we can build complex systems out of it. It's an electrical circuit, it has engineered properties, it's built like a computer chip. Being like an electrical circuit makes it easier for one to imagine scaling up the device if you can get all the coherence which has been done in the last few decades. So on the left is a picture of the device where most of the tan color here is just an aluminum ground plane, and where it's darker is the aluminum's been removed and you see the silicon. And there's this cross in the center that forms a capacitance. And then Josephson junctions at the bottom are forming an inductance to make an LC resonance. And these junctions have a little loop here, and current puts flux into that loop so that you can actually change the critical current or change the frequency, and thus you have a tunable resonator. And we use that to our advantage. Now, this particular Josephson junction resonator can be exactly mapped to a harmonic oscillator, but not a harmonic oscillator, a pendulum, excuse me. And if you remember from the pendulum, as the amplitude of the pendulum gets higher, the frequency goes down. So it's a nonlinear resonator. And what's nice about that means the 0-1 frequency, which is typically about 5 gigahertz, is different than the 1 to 2 frequency, about 4.8 gigahertz. So we can selectively excite 0 and 1 and stay in that qubit state and thus do our quantum computations. Semi-classically, the ground 0 state is just a ground state with maybe a wave function associated with it. And the 1 state has a quantum of excitation with this more or less a harmonic oscillator looking state. And using this, you can use the electrical circuits to understand part of the circuit. You can use simple, slightly nonlinear harmonic oscillator physics to describe how the qubit works. So one can understand pretty readily how these devices work. I first like to talk about just operating one qubit, and this is a time trace where we just have the system relax to the ground state. We then pulse on microwaves at the 0-1 transition. So we do 0-1, 1-0 transitions. And then for a variable amount of time, we then measure it and we get whether the qubit was in the 0 or 1 state at the end. And of course, we measure that about 1,000 times. We repeat the experiment 1,000 times, get a probability. So at t equals 0, we're in the ground state at 1. And then we see a nice oscillation where at 20 nanoseconds, we go to the 1 state, and at 40 nanoseconds, we go to the 0 state. So a 20 nanosecond pulse is equivalent to a knot, and a 40 nanoseconds is a knot and a knot and identity. At 10 nanoseconds here, that's half of a NOT gate, and that's equivalent to a square root of NOT gate. Now, of course, and that's the gate that takes a 0 into a 0 plus 1, this magic superposition state. So, of course, classically, you have no idea what a square root of NOT gate is. However, quantum mechanically, it's very well defined. It's a certain operations. And basically, you build your quantum algorithms over this richer gate set in order to do the quantum calculations that you want to do. So now let's talk a little bit about the hardware. Here's a picture of the chip. The layout is on the left. The squares here or the crosses here are the qubits, kind of as I showed you before. And in between all the crosses on a 2D grid, we have couplers, which we can now turn on and off. And I'll talk a little bit. That was new and how we're able to do that. So we have 53 qubits in a nearest neighbor connected. So each qubit is connected to its fourth nearest neighbor. And that's good for the quantum supremacy experiment, but it's also upward compatible to doing quantum error correction and doing more and more sophisticated things. So this is a good milestone along the way. On the right here, you can see the chip. It's about two centimeters in size. We have a wiring chip here where you can see pads on the outside. The wires come in, and then we have a flip chip indium bump on that connects to a secondary wafer, which basically has the qubits on it. And we have thousands and thousands of bump ons that connect the grounds together. So the microwave engineering is good. And we take that chip, which is here, and we put it into a printed circuit board, which is here. And then we have some shields around it. And basically, we wire bond this to a printed circuit board and bring the wires out to an array of microwave connectors, which are on the outside. And then we just connect that up to our experiment and dilution refrigerator, which you see on the right. So in the center here, you can see the chip mount kind of hidden by all the wires. Then the wires come up with various filters and attenuators. And we also have some quantum limited microwave amplifiers for doing the readout. So this is in the dilution refrigerator at 10 or 20 millikelvin, and that's such that KT is much less than h bar omega, which for 5 gigahertz is about 200 millikelvin. So we're clearly in the limit where we're suppressing strongly thermal effects. So then all these wires, I don't know, about 150, 200 of these wires go up to the top of the cryostat, and then they go down to our electronics right here. And these are custom built D to A cards that we made to have it high performance and inexpensive because we're making a lot of them. And these are giga sample per second D to A's and high precision, low noise. But basically, we're taking advantage of cell phone technologies with both the FPGAs and the D to A chips so that you can build this relatively simply. And then these are connected via Ethernet cable to a computer, which then puts memory in here and tells you the sequence of waveforms you want to put in to do the experiment. I want to talk a little bit about the new device here that were made here and how we can turn off the interactions in a nice way. In the brown here is a capacitor Josephson junction resonator circuit, which forms the qubit. And then between two qubits, we have this adjustable coupler, which turns out to be another just transmon device, a resonator, which we can tune with a line here, put the flux here, and change the frequency of this resonance. This is off resonance from the qubit, so that when the qubit oscillates, it puts some charge and partially resonates this up because it's near resonance. And because this frequency is higher than the qubit, this has an inductive response. So the net charge drive you drive through here looks like a negative capacitance that you could change by changing the frequency of the qubit through here. And then between the two qubits, we add a positive capacitance so that at some magic bias current here, the negative capacitance plus the positive capacitance is equal to 0, and you turn off the coupling. And then we have capacitive coupling with some readout resonators as a standard way that we do that, the field does that. This is an experiment showing how the coupler works. What we do versus time is take one of the qubits and put a microwave pi pulse to initialize one photon and zero, a 1 state and a 0 state. Then we turn on the coupler and we put the two qubits on resonance. So that way the excitation will swap back and forth, very similar to classical swapping in between oscillators. And then we turn that off and we measure on the other qubit if it actually transferred. So here's a plot of the coupler bias, which is its tuning, versus this coupling time. and the population transfer is 0 light and 1 dark. And you see, for example, with zero coupler bias, you get a nice oscillation between 0, 1, 0, 1, 0, 1. This is real data. This is really how nice we can do this now. And then as you adjust the coupler bias, so you lower the frequency of this qubit, then you get greater negative capacitance, and then at a certain bias current, you see it's all white, it's no longer oscillating, and thus the coupler is turned off. And in fact, we go to even higher bias currents here to add more negative capacitance, and then we get very fast oscillation between the two qubits. So we basically have two bias points, an off and an on, that we can switch to by changing the current through here and turn off or on the coupling at will. So with that, I want to talk a little bit about kind of how we go about using the qubits a little bit. And the first thing I want to do is talk about getting the qubits to work well and doing some metrology on making fast single and qubit gates and what's working. And the problem is that you can have a single or two qubits and they can work really well. But when you build a complicated circuit, lots of qubits, lots of connections, of course, a lot of things can go wrong. And you really have to be very systematic about the way you test whether your system is working right, okay? So we do kind of several things we do to test this. First of all, we'll take individual qubits, turn off the couplers, take the neighboring qubits way off resonance, so the qubit's sitting by itself, and then we measure the performance of that. And we usually do something called randomized benchmarking equivalent to that. We do a bunch of gates, see how the errors build up over time. And from that, looking at maybe 100,000 of gates, we can figure out what the mean error of the gate is. And we'll do that individually for all 53 qubits, and you get a kind of a Gaussian kind of distribution. I like to plot the integration of that, so it looks kind of like an error function, just because it's a little bit easier to show the data. And then when you do that for the single one isolated, that's the dotted line here, and the average error is about 0.15%. So you can do, almost 1,000 gates before the system loses its memory. Now you can do the same thing for neighboring qubits by turning on a coupler and checking out how it's working. And that's the light green arrow here. There's a distribution, some better, some worse. Here the mean is about 0.36%. It's about twice as big because there's two qubits, so there's twice as much error. So it's not bad, but it works pretty well. Okay, now, those are looking at isolated devices, but when we're going to do a quantum computation, we're going to run all these gates in parallel because that's what you do with a regular computer in order to make it powerful and fast, and also do a lot of operations before the qubits lose their memory. So what we do is the exact same experiment. For example, with single qubits, we turn off all the coupler gates, and then we just do these randomized benchmarking tests on all of the 53 qubits at the same time, simultaneously. So for single qubits, when we get the probability distribution, that's the solid line, just a little bit worse than single qubit errors, that's great. When we do it for the two qubits, it's a little bit, not about 1.5 times worse. It's a little bit worse, but it's still acceptable, still works right. And of course, we have to work on those gates to make them better, to understand what all the errors are. And that's what the group's been doing for the past year or so and making progress on that. We also have readout errors. Now those errors are a little bit high because there was something wrong with the design of the first chip we tested here. Okay, so we have the qubits, it's working well. We know we can operate them simultaneously, so let's try to run a complicated algorithm. And it turns out the complicated algorithm to run, it's kind of the simplest algorithm to run, is to run the quantum supremacy experiment. And you can see on the right, there's an animation movie that for some cycles, we're doing 53 in parallel single qubit gates. And then the next part of the cycle, there's a line between two of the dots, where we're doing a 2-qubit gate between it. Again, we're doing all the qubits simultaneously. If you look 5 qubits in the center, you can see how there are single qubit gates and then a 2-qubit gate in each cycle. And then since there's 4 nearest neighbors, you cycle through the 2 nearest neighbor gates in some periodic manner. The microwave pulses are about 25 nanoseconds. The 2-qubit gates, they're even faster, it turns out. They're about 12 nanoseconds. Now, it turns out this is a general purpose cycle that you would use to run any particular gate. And the nice thing is that the quantum supremacy uses and tests the most generic gate you can think of. And in fact, what you do in the quantum supremacy experiment is you just take the single qubits, you have known 2-qubit gates, and you take the single qubit gates and you choose, pseudo-randomly choose those gates. And in this case, that's a pi over 2 square root of naught gate, only they're over the x-axis or y-axis or an axis halfway in between them, which is non-Clifford and makes it very hard to compute. So this is randomly chosen, known, but randomly chosen, and then we run the sequence. So how does the quantum supremacy experiment actually validate your quantum computer? And that's the best part of the quantum supremacy experiment. So you run these kind of pseudo-random gates, it mixes up all the states, and basically the states you measure at the end is all possible combinations of the 0 to 1. So there's 2 to the n possible states. And you would think kind of classically that, okay, all possible states, you're going to have a 1 over 2 to the n probability of each state. But that's not what's happened. In a good analogy with laser speckle, where you have a laser light going through some frosted glass and diffusing out, it diffuses out. But some directions, the light is very bright, and some directions, the light is very dim. Where it's light, you've had constructive interference of the waves, and where it's dim, you've had destructive interference. And the same thing happens with the qubit speckle, where there are some states with higher probability and some states with lower probability. And basically, we measure the quantum computer, we're going to measure the high probability states, and then we're going to check by running the circuit through a classical computer if the states we measure are the highest probability states. And we're doing it through something called the cross-entropy fidelity, so that for the states we measure, we take the computed values of probabilities, and if these probabilities are 1 over 2 to the n, because it's kind of classical and no speckle, the fidelity is 0. And it turns out when you go through the mathematics, when you see the exponential probability distribution of the speckle, when it's perfectly matched, you're going to get a 1. In fact, what's nice about this is it's the fidelity of doing the whole algorithm, where 1 is a perfect match, and if you have any errors at all, you get a 0. So let's say you just programmed your classical computer wrong, and you put an extra NOT gate in there, then your fidelity will all be 0. So it's a really good system check to make sure you're doing everything right and your qubits are doing right, and you just basically measure the probability that you made any error at all. And that's really useful for system validation, because you want to know if it works. Okay, so you work on this for a while and get it to work, okay, and this is the final data. And this is data for running 14 cycles, so that's 14 2-qubit gates and 14 qubits and 15 single qubit gates on each qubit. So if you take 12 qubits, that's about 250 gates total. And when you do the experiment and tune everything up right and get it to work, then you get the red circle, which is a fidelity about 0.4. So that means 40% of the time you ran the algorithm without an error for 250 gates. And of course, as you increase the number of qubits, the fidelity goes down because there's more possibility errors. It's going down in an exponential way, which is what you want it to do. It's not like it crashes all of a sudden because you did something wrong. It just goes down in a nice way. And then here we are at the final point at 53 qubits, where it took about 5 hours on a Google data center, lots of cores to check that everything was okay. Okay, now, so that's great. Everything's working nice. There are some check experiments we do. One of them we call the patch circuit, where we just turn off the couplers in the middle of the circuit. So these are isolated qubits now, which of course is exponentially easier to simulate because these two sides are not entangled anymore. And when you do that, you more or less get the same data. And then you can do something in between where you turn off some of these gates, but not all of these. And there's some simplification things you can do. And again, you get more or less the same data. It's more or less the same number of operations. So it's equivalent. Okay, so that's great. We have something that takes a long time to compute at 53 qubits. We want to go into the supremacy regime. And in fact, going to the supremacy regime, we just take the order of which we do the 2 qubit gates. We change that a little bit. And it turns out there was a mathematical trick here that made it simpler to compute. And when we get rid of that trick, now we can't simulate it anymore because it takes years or millennia to simulate it, okay? Now we can estimate, okay, and here it's the number of cycles from 12 to 20 with 53 qubits. So it's kind of the other axis, the depth instead of the width axis. Now, of course, you want to know, would you see quantum supremacy? So what you do is you repeat these experiments for the patch circuit, fully cut or partially cut Elided circuits, and that makes it easier to compute. And when you do that, you get the blue and green, and these are 5 sigma error bars. So it's statistically significant apart from 0. It's real. And since these particular Leiden and patch acted as proxies to the full circuit, we expect that if we could run the quantum supremacy experiment, our red circles would line on top of that, and then everything would be okay. So of course you can't do that. It takes too much time, and we have the data out there in case, as a computer science challenge, in case ever anyone wants to check if we actually did things right. And of course things will get very hard very, very quickly. So everything works great. We see quantum supremacy. It kind of behaves properly. I now want to talk a little bit about the quantum science results from this. And there's a lot of things we can say about quantum science and quantum computers that are really new here. And one of the big things we did in the last one is so that we have the same fidelity, whether we had a full circuit or an Elided or patch, and even the predicted circuit, and I'll talk about that in a second, was the same. And what this means is that the errors we see in this very highly entangled, complex computation is basically independent of the amount of entanglement and computational complexity. Which, when you think about it, is kind of amazing that somehow quantum mechanics doesn't get super sensitive to it. And of course, this is the assumption you make in order to build a powerful quantum computer. So the fact that we tested that and it works properly is really, really good. The other thing I want to talk about is if you look at the black lines, going back to the previous slide, the black lines is what we predicted from our measurements of single qubit errors and 2 qubit errors. So measuring single qubit errors and 2 qubit errors, we can predict what's going on with 53 qubits in this very complex state. And we predict it using a probability prediction, which is basically your high school, statistics probability course, where we just multiply all the fidelities of the individual operations. And that just simple thing works, a simple probabilistic. Even though there's coherence in the system, that's good. And again, this is the assumption you make in error correction, and it's great to see that it works. And there's some things we're doing in the algorithm that helps this work, but it's nice to see there's nothing fundamental going wrong there. Quantum mechanics works at this 2 to the 53 or 10 to the 16 Hilbert space. Previously, it was tested maybe at 1,000 Hilbert space. So we did something 10 to the 13 times bigger. And it's not very often in physics that you go into a regime by 10 to the 13 and you don't see something new happen, which is good in this case. Finally, you can test the model of digitized errors. This is the plot of the cross-entropy fidelity for, I think, 14, 16 qubits or so, where we've taken in the simulation, we put a phase change in the simulation somewhere between 0, which is no error, pi, which is a full error, and then back to 2 pi, which is no error again. And then when you look at the cross-entropy fidelity, it goes up and down, and it's 0, where you have 1 error, as I told you before. And if the curve actually follows a cosine squared behavior, which is basically when you have this continuous error, it's basically the probability that you had an error from that. And this basically is the basic assumption by error correction. And it's really nice to see that this basic assumption of probabilistic errors is correct when you have an error just embedded into a really complicated circuit with all this entanglement. This simple idea still works. Okay, so all that is good for the future. That we should be able to continue and try to do more complicated things. Now, since we got the quantum supremacy experiment, people at Google, of course, have been working hard to improve it, and there's some new papers coming out. The theory group will have been working on algorithms, have done a series of nice algorithm demonstrations that take advantage, not so much as the number of qubits, but the quality, the low error rates that you can get out of these qubits. And, there's quantum adiabatic optimization. There's a Fermi-Hubbard paper that's coming out. Let me talk here about quantum chemistry, which I think is going to be one of the, surefirest, for sure, applications for a quantum computer. The basic idea is that the exponential difficulty of quantum chemistry in a classical computer comes from the explosion of the Hilbert space. And if you can map it to a quantum computer, then you can take advantage of the quantum computer to do your calculations for you. So there's a long series of theory and some experiments that are going on to doing that. The theory is basically you first compile whatever chemistry you're doing to qubits using Hartree-Fock fermionic operations, figuring out a goods coupling sequence and a suite of measurements. And then from all those, you get parameters for your gates, and then you run it on your quantum computer. So this is a case of H6, where we have 6 qubits and some swapping gates in between, and then a suite of measurements between that. And kind of what's interesting is with your suite of measurements, for example, none of these operations here being swapping operations, they don't change the number of excitations. So you can correct imperfections of the circuit, for example, by only looking at the output where there are 3 ones given here. And there are some other things you can do to improve it. And what's amazing is even with fairly complex circuits, you can get very high fidelities by correcting for excitation law, measurement bias, and other things. And then, of course, you do a variational optimization to get the final answer. So here's an interesting example, hydrogen-12, that doesn't exist in nature, but you can certainly simulate that, and we think that's kind of a good benchmark problem. In the black lines is what you expect, and in the blue are the measurements coming out of the quantum computer, and the errors are down here. And you see it follows what you expect very well, and actually has fairly low errors. And once you get down to, I think it's H6 or H8, the errors are then below what's called chemical accuracy, and it would be good enough for chemists to use in real world applications. So there's some other experiments that they did with transition state theory and in trying to find an energy of an intermediate state on a real molecule in the paper here. But I think what's interesting about this is given the good quality of the qubits, they've been able to double the number of qubits or electrons prior to what they have done, and about more than 10 times the number of gates. So this is a pretty big advance for the field. And, again, I think this is good. As more powerful quantum computers come on board, then we can do this. And these problems have thousands of gates at this point, and you can really start running quite complex algorithms and really test whether the algorithms and your techniques for using them work properly. It's still not, you can still simulate that on the classical computer, but you can test complex ideas with this. In order to do that, we have the Sycamore chip, we have our programming language Circ, and then this kind of compile chemistry to qubits, open fermion. So Google, as well as a bunch of other people, are developing a suite of software tools so that people can do complex experiments. And we're hoping to get this out in the cloud soon, and Google's hoping to do that, and then people can try your own algorithms and try some new ideas. At that point, I'm going to start wrapping up here, and just, of course, we've seen quantum supremacy. Quantum computer is powerful, and next step is let's make it useful, and let's make it transform society. Because it's going to take a while. That's much harder, but at least we have motivation that all the quantum mechanics should work properly. As people start looking at the various quantum computers and thinking about using them, I just want to remind everyone that quantum computers really are not a commodity in the sense that performance matters greatly, right? The performance is exponential with the hardware of your system. So if your hardware is a little bit better, then everyone's going to want to use it. Of course, quantum computers can be different. That's good. But this is really pushing the hardware people to just get their qubits working well. And I think it'll be interesting in the next few years as people use quantum computers and test them to kind of see what matters and what doesn't matter and practically understand that. We think there's a lot of breakthroughs that happened in the Sycamore device. We know how to make things better, and that's happening, and some papers will be coming out from the Google group. And in terms of customers or programmers or algorithm developments, we showed one algorithm with quantum supremacy, but we're hoping this will motivate people to work really hard. And maybe one idea way, maybe with some hardware improvements, maybe we can come up with a NISQ compelling application and have this field really take off once we start doing something very useful with it. Finally, this was a big team effort at Google to do this. And I want to thank everyone, especially a big hardware team that worked very hard and came up with a lot of clever ideas to get this experiment to work. And it was really the team effort that enabled us here. Okay, thank you very much.
Thank you very much, John. It was a great talk, fantastic for covering all of these things.
Can you hear us?
Yes, I can hear you. Thank you very much.
Just checking, yeah.
Okay, great. So there was a lot of questions in the chat, but it's amazing that people are already answering a lot of questions, something. So thank you very much to all the people who are also in the chat and answering the questions. So let me start with the general question, and then we can dig into the more. We all want to know the burning question of the, how do we go with the scalability? What is the roadmap to scalability? If you can give us a bit of a vision about where do you think superconducting roadmap to the scalability will come up with?
Yeah. So once we got the quantum supremacy working, I started really thinking hard about scaling. And at first, it was kind of very depressing to think about it. But then finally, I came up with an idea. And the last summer, I kind of understood in my mind how to scale to 1 million qubits, which with error correction and good enough qubits, about 0.1% error, you could then build a powerful quantum computer and solve chemistry problems. So that was very exciting. And the Google group has taken this and done some road mapping and figuring it out. Unfortunately, I wanted to write a paper on this, but unfortunately, the Google group wants to be a little bit quiet about it for the next few years. But there is a plan. It looks hard, but doable. And it will remind you a little bit of a high energy physics experiment, put it that way. So the details will be coming out in the future, but there is something. And I'm sorry I can't say more about that. I would love to, but
we trust you.
They don't want that.
We trust you. That's great news. So maybe, I mean, just staying on that, I'll ask another question, that there is this tension between getting the best in terms of application and end user application out of the NISQ device that we have, and putting our effort to get the error rate low and go the fault tolerance, etc. And these are two different strategies. And of course, everybody can choose them. And I would like to know your view on that. You already mentioned it in your interview about it. So this trade-off.
So I've talked about this, how the target, if you're going to build, you're probably going to build a surface code because that's the highest, or a near variant of that, since that's the highest threshold, about 1%. So you want to be about 10 times below that. So the target value is 0.1%. And then if you make a lot of qubits, you can do error correction. So that's what we were targeting. That's what people are working on. And they're making, the qubits are getting better. We have to improve the coherence. The nice thing about the coherence is that T1 time of the Sycamore qubits was only around 20 microseconds. And people have made 100 microsecond devices before. So, we were not focusing on that. And we're just focusing on making a big system. And now they have to make the coherence times longer. But I think that can be done. It just may take some effort to figure out exactly what's going on. In fact, one of the things I've done since leaving Google is I have a theory now on how to sort all that out, and I think I know what the culprit is. So I think we can make better qubits in the future. And you have to get the gates calibrated well and whatever, but it's not guaranteed, but it looks quite promising that all that can happen. And of course, like I say, doing the scaling, that's going to be hard. So, but there's a definite plan ahead.
Okay, another one about error correction. How far do you think superconducting qubits could go? Not just correction, I mean error control. I mean reducing the level of error or maximizing the fidelity of the qubits. And another question would be, how do you think this error level will be stable as we grow the number of qubits in those architectures?
Yeah, so to make the qubits better, you have to do two things. Is you have to make the coherence times longer, and you have to improve the control. And the group has been working on control for more than a year, and they're making progress on that. And I think they're making some progress on coherence. And it's just a matter of, figuring out all the details there, the minute details. So, you just have to work on it. You see, I think it's doable. Some of the gates are pretty close to our targets, and so the best gates are very close. But of course, it's the average that matters. So you can say that there's almost an existence proof that it's possible, but you do that. Now, whether things go bad when you build a big system is, of course, the big question. And what happened is when we built Sycamore, we knew that there could be a lot of problems, and there was a lot of design with this flip chip and the way that we did the design to minimize crosstalk. And then what I would say from the Sycamore chip is that I think that has been more or less solved to a fairly good degree, and that we have to make our qubits way better to actually see if there are any errors there. So you have to remember that, we calibrated the 1 and 2 qubit group gates, and then we just run the full algorithm, right? It's not like you're tweaking it up afterwards in some way. Now, this is exactly how you want to use a quantum computer, and it works. But you have to remember that the group has been working on this, more than a decade, figuring out how to do those kind of calibrations, and have a huge amount of software to understand that. And that's the reason why it works so well.
I guess that's already answered one of the question in the chat, because it was asked by somebody that why Google choose superconductory approach over any other approach, So what was the pro and cons? To some extent, you already say it, decade of experience, but I don't know if you want to add something to that. Why superconductory?
Let me just add to that. Everyone thinks their own qubit system is the best, and that's great. You have their own things. Of course, think about superconductors. In superconductors, it's not like any one metric is really great, the best in the world. It's just that everything kind of works and nothing is really horrible. And that way you can design the system so that everything works well. The other thing that is useful, maybe not so well appreciated, that our qubits are relatively large, about a millimeter in size. And that means you have room for your control circuits and control wires to get into the qubit. And this is why you can't make a quantum computer out of atoms and molecules. You can't get the control signals in. But these are about a millimeter size, and you have enough room. Of course, if you build a million qubits, it's going to be a pretty big computer. But okay, we'll work on miniaturizing later, I suppose. So big size is actually kind of helpful, which is not necessarily appreciated by most people.
Okay, and by the way, could you explain us about the past roadmap of Google, why we went from 72 qubit, it was a Bristlecone architecture, early 18, to 53.
So in the 72 qubit Bristlecone, we had fixed capacitor couplings, and then we just brought things in and out of resonance. And the problem is when you bring it out of resonance, you really weren't turning the coupling interactions completely off. And it was kind of complicated and hard. And then by doing the adjustable couplers, you could really turn it off to eliminate your errors. Your frequency excursion was less, and you could also make faster gates. So because with the couplers, I have a wire to each couplers, you had more wires. So we had to scale back to 53 in order to not have to do more wiring in the refrigerator. So we were constrained by that, and 53 was enough to do the quantum supremacy experiment. And the Google group now can build more qubits, and there's no problem with that. It's kind of funny, you're trading off wires, which people don't want to have too many wires. Our idea was just wires are okay, we know how to put them in, and we'll do anything for good coherence and ease of control. And and that gave us some good results.
So in a way, the 53 qubit architecture from Sycamore was more complicated than the 72 qubit without the couplers. That's it.
Yeah, and if you think about it, there's almost 150 junctions or transmons in it. So it is more complicated, but you're using it in that way. Okay. But yeah, the complexity and the added fabrication difficulty is worth it if you can turn off the interactions and make better gates and make it easier to calibrate.
So a few more questions on superconducting before we move on. So people asking, when can we use SIR commercially? And another question is about what do you think the number of the logical qubits we can get out of your envision 1 million physical qubit? These are like two quick questions.
Yeah, so in terms of using Sycamore, that's of course up to Google, and they're having a cloud. And I think if it weren't for COVID, it would have been launched by now. But there are it's being used internally, and it's being used by some preferred collaborators to kind of test out the system. But I think it's going to happen, fairly soon. But I don't want to speak for Google because I don't know what all their constraints are.
Sure.
But in the end, I think it'll be really nice, high performance system. And there's certain things that Eric Lucero is doing with the building that's really nice, so make it more reliable. In the million qubit machine, you're focusing on about 1,000 physical qubits for one logical qubit. And those are kind of the numbers you get out of the 0.1% errors. And of course, you have to see what the errors are, maybe more or less than that. And then naively, that's 1,000 logical qubits, but you have to do a lot of T-state distillation So in the end, that's maybe 100 or under 100, 200 logical qubits for 1,000,000 qubits. And again, you have to do a lot of research to do that. Just one thing about the logical qubits, there's some papers that will be coming out of the Google group about doing error correction. And in particular, one of the things you should worry about is whether you leak out of your 0 and 1 state to, say, the 2 state, because that will represent correlated errors. And the Google group has some nice data on that I think is very kind of new to the field and shows, the problem and what you can do to mitigate against that people will be very interested in. So that should be coming out soon. So be thinking about that.
Okay.
One question about your slide on the applications that were published in April this year, the R3 fork and the quantum chemistry example. How would you rate the performance of those two apps? I mean, is it a quantum advantage? I suppose it's not a quantum supremacy. How can you rate that compared to classical computing? Because it's a completely different experiment than the quantum supremacy one.
This is still easy to solve with the classical computer. This is, let's say 10, 20 qubits, which you can easily simulate. I think the really interesting thing is that they're doing algorithms with 1,000 gates. And what you can do is you can take some complex algorithm that you want to do and kind of strip it down to 1,000 gates, and then you can do a realistic test. It's not like 2 qubits with couple gates. We're past that. So now you can really test complex algorithms and see what's going on and kind of learn to play with the algorithm by using the machine. So that I think that's really exciting that they're doing things at that level. And of course, it's like driving a Ferrari. You have to learn how to drive the quantum computer properly, and that's what people have been learning and trying to automate that so it becomes like driving driving your Honda. Okay, but it takes some time to figure out how to get all the performance out of it. And it's very interesting time for people to figure that out.
Talking about your Ferrari, it seems that you're changing your car. Now you're switching to silicon. Can you tell us a little bit about your new car design?
I left Google. Things weren't going so well for me professionally. What I want to do now is I want to help someone build a quantum computer. So one of the things I'm doing is I've come up with 4 big ideas, kind of solutions, the showstopper ideas for superconducting qubits. So I hope to write that up soon and hopefully help that field. And then Michelle Simmons here invited me to come visit. I always wanted to learn about silicon quantum computing, so I'm here and learning about it and asking very basic questions, which turns out to be a little bit useful, and we're learning some things. So it's good to contribute, and it's good to learn about another system. And I'm thinking about how to build a quantum computer from now a different manner, and that's good. So I'm here for 6 months, and I'll then come back to Santa Barbara, and I'm planning to go to Europe for maybe 3 months next summer on another kind of sabbatical. So it's a nice time for me to visit other groups.
That's good to know. So, but because we have a panel actually coming a bit later, which is talking about various qubits, so talking about this move that you're discussing, do you envision there is a lot of commonality that in design that it comes in between various qubits? What you learn about superconducting might be useful for silicon and vice versa. So.
There are some common themes like noise and understanding noise and how important that is, and there's charge noise instead of flux noise, or trying to figure that out. But I would say the other interesting thing, talking to Michelle Simmons, is how to organize and manage a group that is partly in the scientific realm and partly in the engineering industrial realm, and what are the things you do to bridge that gap and stay creative, but stay focused on your final product. And I'm having a good time talking to her about that. So in the future, after I've thought about these and worked it out with Michelle and others, that's something I can share, with other groups too. I think it's a very interesting kind of management issue as well as a science issue.
By the way, I see on the chat that you may have some invitations from Grenoble, for example.
Yes.
We would like to see
Yes.
you in your next sabbatical because they are also.
Yes. I'm very interested just to go around and learn about systems and try to help. And of course, Australia is a very beautiful place to visit. So, and I get 3 summers in a row by coming to Australia. So I like that. So thank you.
Okay.
Yes.
Okay.
Talking about invitation, somebody is also asking, John, why are you not working on ion trap? So there is lots of bits for you. Why not ion trap?
Yeah. Ion traps is the one system that I would like to learn more about. So yeah, that would be good.
Fantastic.
We would have a broad question with regards to scalability. How would you rank the scalability potential of each of the known qubit types we have right now? I mean, the trapped ion, cold atoms, photons, silicon, superconducting.
So let me be a little bit diplomatic here and say that scalability is a hard issue because you have lots of system engineering constraints. And there's lots of things that people haven't invented or even imagined so far that could change it dramatically. So I would never say anything, to say that, this way won't work, okay? Because we just don't know. But the one thing I would say in terms of scalability is that large size really helps you figure out how to build your control system, into your qubits. Because in classical digital, you don't have a control system. You have a voltage, 0 or 2 volts or something, and then you power it up and you have your logic. Whereas in quantum computers, you have this very intricate control system that actually, if you just think about the information content of your control system, it's quite high. Now, in principle, you might be able to simplify that, but right now, all these waveform generators are very complicated and that. So I would say having some size to your qubits works to your advantage in order to build the control system. But again, if you could build a really good qubit that has a simple control system, then it could be small, and then it's going to be another optimization problem. But it's something to think about. I think it's fundamental.
We just don't want to stop this. There is more question coming in the chat. It was very exciting. Maybe I just put the last one before the break, which is somebody asked, do you believe topological approach can be implemented sometime in future?
Yes, the topological approach is very interesting, of course, because it would minimize the number of qubits. And, I'm anxious to see about that. And, obviously I'm in Santa Barbara, so I can find out from Station Q. So it's a very interesting approach. I think the problem is the thing that I worry about is the topological approaches might be sensitive. These states might be fragile and sensitive to some practical error physics. For example, if there's any stray quasi-particles hanging around your system, which we think are in superconductors, then that might poison the topological states. And of course, people might be able to get around that. But you're looking for an exponential suppression of errors, but you have to worry about all the error mechanisms. And if it's anything we've learned in the last few decades, is that you can write down on paper what your qubit system is going to look like, and it's going to look really clean and nice and great. And then you do the experiment and you see all the dirt effects, and then you spend a decade or more figuring out the dirt effects and hopefully working around them. So it's just hard, and people just have to do the physics. But that could be a real game changer. So of course, it's very interesting.
Great. Thank you so much, John, for this wonderful talk, for spending your time answering all the questions. It was great having you, and hopefully see you soon in France.
Yes, I hope soon we'll be able to travel.
Yeah, the hotel room is already booked. You can come.
Yeah, thank you. Yes, thank you. I appreciate it. Okay. Have a nice morning.
Thank you.
Bye-bye.
Thank you. Bye-bye.
So we're going to have a short break, a 20 minutes break. But do come back. We're going to dig into the qubits even further, and we're going to do some more physics. But also, if you want to stay online, there will be some surprises. So see you soon in 20 minutes.